The next presentation is by Kathleen Petit. According to the title, there is a thesis here that Fagus sylvatica is facing vulnerability to climatic change. And the talk would be on how genetic diversity can be used to reduce this vulnerability. So, the floor is yours.
Thank you, Phil. So, I will present to you the last part of my PhD, the third chapter, in collaboration with François Lefebvre, Hendrik Davy, Hans Verkerk, and Silvio Du Muratorio. So, as many people present to you yesterday, in a population you can find a gradient of phenotype, and one phenotype will correspond to an optimum of fitness. In a stable climate, we expect that the optimum fitness corresponds to the higher frequency of this phenotype found in the populations. And in a changing climate, we expect that a change of the optimum of the phenotype, but this change can be local adaptation can be used to have changing in this optimum fitness. But in a rapid climate change, this exchange of genotype between population will not be optimum to allow to local adaptations for populations. If you have some question, Julie Gausser explained better this slides. When you don't have a good local adaptation, this can lead to population extension, and in the future climate change, we expect that mortality in response to be higher, and there are two main physiological mechanisms leading to this mortality. So the intensity of the water stress can lead to hydraulic failure, and to avoid this hydraulic failure, the tree can close their stomach and dig in their reserve to survive. But if the drought is too long, they can die of carbon starvation. You have several physiological traits involved, and we can measure percentage of loss conductance, the non-structure of carbohydrate concentration for the carbon starvation, and the water use efficiency for the both mechanisms. Another mechanisms that it's expected to increase in the future climate change is the decline in response to late frost. Here you can see the bird burst date of several species, and here the safety margin date is. This is the number of days between the last late frost observed in the populations and the start of the bird burst date. But with warmer winter, it's expected that the bird burst date will be earlier, so a lower safety margin can be found. Here, in this study, we try to answer to this question. So, how within and between population genetic variability affect beach risk and mortality in response to drought and late frost? How will this change with climate change? And how management strategies accounting for within specific variations can mitigate this vulnerability? So we used a model able to take into account modality of risk, so the hazards, which is the climate, and the vulnerability of tree through sensitivity and adaptability. This model is Castanea, which simulates fluxes of carbon and water between the tree, a mean tree, and its environment, and give us a carbon and water tree stock. Here we use soil data and climate data at European scale and focus on adaptive traits. Three of them. The bird burst and we implement genetic variation through the FCRIT-BB, which is which is a sum of temperature before a bird burst. The water use efficiency, through the G1 max, which is the slope of carbon concentration on carbon on water conductance, and the percentage of loss conductance with the slope of this relationship. So I will focus the method on one adaptive trait, the day of bud burst, here to explain you how methods. So here you can see 9 populations across Europe. Here a gradient of the genetic traits and the day of bud burst corresponding. Here you can see so the between annual plasticity, several points, and here the phenotypic plasticity for a given value of the F-CRID-BB. And then here the within population variability at a one. And we used to simulate the between population variability, we use the study of Robson 2018, which show that for population at high latitude and altitude have earlier bud bursts in common garden. So this is how pattern at European scale. For the adaptive trait water use efficiency, so that you have to know that lower J1 max give a higher water use efficiency, so water conservations. And we use a study of AJECT et al. 2016, where they found that the lower G1 max for populations from arid climates. So here you can see the pattern we simulated across Europe. Then the last adaptive traits, the percentage of loss conductance. So this is, we decide to characterize to do a genetic variation with the slope of the relationship, and that you have to know that with a higher slope, the start of cavitation process will be later but faster, and with a lower slope it will be the reverse. You will have a cavitation process starting earlier but slower. And in the same study of AJECT, they didn't find a significant genetic variation between populations, so we choose to take 3 values of the genetic parameter traits. I will present to you the finite design of the modelization. So we choose to take one mean trait as a reference mean tree, and choose to mix all the adaptive traits and their clinite pattern for each genetic parameter, the minimum, the mean, and the maximum. So in total, 27 genotypes at each grid point, and the reference mean tree. Under the current climate and 2 future scenarios. In addition, we simulate management scenarios according to 4 main ecoregions and country management habits. In total, we had more than almost 2 million hours of simulations run for this project. For the first result, main result is in a purple here is a variable area simulated with the reference tree, and when we're taking into account of genetic variability, new variable area appears. In the future, this new variable area and the reference mean tree variable area decrease, but we still have a good spread of the species. And when we take into account of the genetic variability in our simulations, we have a decrease of risk of mortality than when we compare with the reference tree. When we focus on genotypes minimizing the mortality risk due to drought and life frost, we found for the G1 max genetic component that the minimum gives a lower risk of mortality, which meaning that the higher water use efficiency prevents drought, we found for F-CRIT-BB the maximum value prevents late frost, meaning a later bud burst. And we found for the PLC slope genotype the maximum of the value meaning that a higher PLC slope limits cavitation under weak truth. And I don't know if you can see in the back. Here we have other genotype minimizing the mortality risk, and all are located in the marginal south area. And this is a longer vegetation seasons and a low PLC slope, which limits the cavitation under severe drought. And when we focus on the genotypes maximizing the growth, we have water use efficiency are depending on the area. Early bud burst, so the value of the genotype giving the longer vegetative seasons as a genotype maximizing the growth, and no influences of the PLC slope. And we don't have anymore a particular pattern in the south of margin. So a single genotype does not optimize both growth and survival. When we are looking the entire area value, with composite risk index integrating drought and late frost, on the maximum J1 max and the minimum J1 max, which are the weaker genotypes and the stronger genotypes, you can see under the current climate, the mortality risk is lower for the mean J1 max, and under climate change, so in the future climate, the mortalities decrease in both cases. When we take into account management, so the gray box plot, there are no differences between for the mean J1 max between current and future climates during current without management and with management, but the beneficial trends is more pronounced for the more vulnerable genotypes. So you can see here a decrease of mortality risk when management is applied. So the take-home message I would like to remind and that considering genetic variability in management and conservation practices can mitigate the risk of mortality due to late frost and drought under current and future climate conditions. The genotypes minimizing risk of mortality differ from those maximizing the growth. Actually, we found a little trade-off between genotype of maximizing the growth and the risk of mortality, minimizing the risk of mortality. So the maintenance of genetic diversity is essential for the sustainability of populations. And the management reduces the risk of mortality and the difference of risk of mortality between genotypes. So an innovative management practices with transfer of genetic material can be tested with this approach that we are currently analyzing simulation on this. Another point that you have to have in mind is that our model is very optimistic because it don't take into account extreme events and biotic interaction with the mortality. Thank you.
Thank you very much, Kathleen. Questions for this presentation? Well, I'll make the start then. I've noticed that there's this very interesting trade-off, of course, between mortality and growth. But would mortality be induced before reproducing age or after? Because that's a big difference.
Well, I didn't focus on the reproduction part, but when one of the mortality threshold was crossed by the tree, I removed the viable area. So when you see on the map was all the viable area, which means that the population can reproduce in these points. So the trade-off is existing.